Hi everybody, welcome to the start of our Sun and Stars unit. In this video we're going to go over some preliminaries involving relativity that you need to know for astronomy and some of the consequences, even though a lot of them are unrelated to our discussion of sun and stars. So first of all, I should mention that there is definitely not sufficient time in a course like this to go over all of the ramifications of relativity. So we're just going to go over a very brief introduction. If you want to learn more, then you should probably take a course on relativity in college, because that's part of the modern physics curriculum, and that's something that you'll typically hit if you end up deciding to become a physics major or astronomy major. But in any case, special relativity is essentially what Einstein figured out when he was 26 years old. When he was 26, the year 1905 was his year of miracles. He discovered not only special relativity, but he also showed that that implies E equals mc squared. He also came up with an explanation that turned out to be correct for why the photoelectric effect occurs, showing that light behaves like particles. And he also showed that Brownian motion proves that atoms exist. So quite a lot of accomplishments in just 1 year. Any one of those would have made him famous for a very long time, even if he had never done anything else for the rest of his life. So, in any case, special relativity deals with flat spacetime. In other words, it's not dealing with the general situation where gravity is an important factor. It's dealing with the special situation where you can pretend that gravity is not around. So special relativity, no gravity. General relativity deals with the general situation where you include everything, including gravity. And general relativity is a lot harder than special relativity. I mean, most of special relativity can be understood just using a little bit of algebra and a little bit of geometry and some logic, whereas general relativity brings in a whole lot more math, which is why it took Einstein a lot longer to come up with general relativity. He had to learn about tensor calculus and differential geometry. Well, really the same thing, but in terms of applying that to his special relativity. So before the time of Einstein, people like Galileo and Newton believed that space and time were absolute. They believed that if every observer in the universe had good synchronized watches, then they would measure precisely the same distance between two events and the same time between their occurrence. And Einstein showed that this cannot be the case. He showed that space and time can't be absolute between moving reference frames, and part of this has to do with the fact that the speed of light must remain constant in any inertial reference frame, that is, any reference frame that's moving at constant velocity. And one of the arguments even before Einstein had made these realizations was that it's like, well, wait a second, consider two stars that are very far away moving around each other. If the speed of light changed from one reference frame to the other, then the star that's coming toward us would come toward us with faster light, and that light would end up passing the light that it had previously emitted when it was going away from us, since they're orbiting around each other. And the stars would appear to kind of chaotically shift back and forth in the sky. And that does not happen. The shiftings in the sky are quite smooth and easily tracked. So even before 1905, it was realized that at least the speed of light appears to have the same speed in all inertial reference frames. Einstein simply said that it actually does. And as a consequence, space and time themselves are what are different depending on the reference frame. So first of all, moving lengths appear contracted. In other words, they appear shorter according to moving reference frames. And when I say moving reference frames, I'm talking about a reference frame that is moving with respect to the length. In other words, if a ruler is moving by you at a high percentage of the speed of light, that's the same thing as if the ruler is at rest and you're moving by it at a high percentage of the speed of light. In both situations, you see the ruler moving, and in both cases, the ruler is going to appear contracted. And all of those reference frames are completely equivalent according to the laws of physics. That is actually Einstein's first postulate, that all inertial reference frames are equivalent. The laws of physics are the same according to all inertial reference frames. It's really just an extension of Newton's first law, which itself is just a restatement of the Galilean law of relativity. And even Galileo didn't come up with that. Nicola Resme realized this back in the 14th century. And who knows, probably people before him as well. But in Newton's first law, we're basically saying that objects maintain constant velocity in the absence of an unbalanced force, but really that's just, if you think about it, it's just another way of saying that all inertial reference frames are equivalent. Time periods appear longer according to moving reference frames. If I move by you at a large percentage of the speed of light, then that is going to mean that you are going to see my watch running slowly. Similarly, I am going to see your watch running slowly as well. So that ends up leading to a very interesting paradox. But before we get to that paradox, let's look at another paradox in relativity involving length contraction. It's the famous pole in the barn paradox. So the longest possible length that anybody can measure is one that is measured in a stationary reference frame. In other words, reference frame where the events of measuring it are going to occur at the same speed, so to speak. In other words, if I want to measure the length of a ruler, then if I am holding the ruler, that ruler is not moving with respect to me. So that ruler is going to have its longest possible length. However, if somebody else is going by me at 80% of the speed of light, they're going to observe that ruler to appear shorter, assuming that they're moving along the direction of the ruler's length. Now, here comes the paradox. Let's say that Alice and Bob are trying to figure out a way to store Bob's pole in his barn. Now, Bob has a 20-foot long pole and only a 10-foot long barn. So Bob tells Alice, it's like, okay, I have this wonderful idea. What I'm going to do is I'm going to run at 86.6% of the speed of light, which will give me a length contraction factor of 2. The length contraction formula is that the new length is equal to the old length times the square root of 1 minus v squared over c squared, where v is the speed of the object and c is the speed of light. So if I have, plugging in 0.866c for v there, squaring that gives you 0.75, 1 minus that is 0.25, and the square root of that is 0.5. So if you run at 86.6% of the speed of light, things are going to appear twice as short. And in the case of Bob's pole, Bob is telling Alice, okay, if I run at 86.6% of the speed of light while carrying this pole, then you can slam the barn door behind me right as the back end of the pole goes through the barn, and the pole will be in the barn because, according to you, the pole will be 10 feet long. It's still going to be, the pole will be 10 feet long. The barn will still be a 10-foot long barn, so therefore the pole will be in the barn. But Alice says, well, wait a second. No, that can't be right because according to you, the pole is still 20 feet long, and it's the barn that's getting length contracted. So according to you, you're going to be trying to fit a 20-foot pole into a 5-foot long barn. That's not going to be possible. So the question is, who is right? And the answer is, you cannot store the pole in that barn because even though Alice sees the pole inside the barn when the back end of the pole is in the barn, thing is, those events are taking place in different reference frames. And not only are they taking place in different reference frames, the events are taking place at different locations. In other words, one event would be the front end of the pole reaching the front end of the barn, and the other event would be the back end of the pole reaching the back end of the barn. And one of the other consequences of relativity is that two events that occur simultaneously in one reference frame are not generally going to occur simultaneously in another reference frame. In other words, even though Alice might observe both ends of the pole in the barn simultaneously, Bob will have already had the front end of the pole rush through the front end of the barn, bust through the front end of the barn before the back end of the pole has reached there. So there's going to be a disagreement between the simultaneity of events. And in any case, if Alice tries to suddenly shove the back end of the barn's door closed, then right after that, soon after that, the news of the pole busting through the front end of the barn will reach her. So that's the kind of logic to keep in mind in relativity. Now, in the case of time dilation, this leads to another very interesting paradox, because if I say your clock is running slowly, and you say that my clock is running slowly, it's like, okay, who's right? Well, consider this paradox. Let's say Bob and Alice are twins, obviously not identical twins, but Bob and Alice are twins, and Bob is sent away on a rocket ship at, let's say, 99% of the speed of light. So you do 0.99 squared, that's 0.9801. 1 minus that is 0.0199. So we'll call it about 0.02, but sure, 0.0199. In fact, actually, let's round that to 0.0196, because that actually happens to be exactly the square of 0.14. And 1 divided by 0.14 is 7. And so what we realize is that somebody moving at 99% of the speed of light is going to experience a length contraction factor of 7 and a time dilation factor of 7. Lengths will appear 7 times shorter, times will appear 7 times longer. So Bob is going to go away at 99% of the speed of light toward a star. Let's say, we'll say that the star is, according to Earthlings, 14 light years away, whereas Alice stays here on Earth. So if the star is 14 light years away according to Earthlings, then according to Earthlings it will take Bob basically 14 years to get there and then 14 years to come back. So the length of Bob's trip will be 28 years according to Earthlings, including Alice. However, we say, okay, well, Bob's clock is running slowly. So according to us, Bob is going to be gone for, it's like, okay, his clock is going to be running slowly. He would seem to age slowly. He would seem to age slowly by a factor of 7. So instead of aging 28 years according to, like people on Earth do, like Alice does, he would only age 4 years. Well, here's the paradox, though. It's like you might seem like, well, okay, fine, Bob just ages less than Alice. The paradox occurs when you consider the fact that according to Bob, it's Alice who has slowly running clocks, and she is the one aging more slowly. So, first of all, according to Bob, he's only gone for basically 4 years, and so time dilation factor of 7, according to Bob, Alice should have aged only 4/7 of a year by the time he gets back. Okay, well, who's right? Is Alice right that Bob ends up aging only 4 years while Alice ages 28 years? Or is Bob right that Bob ages 4 years while Alice ages 4/7 of a year? So it turns out there is a solution to this paradox. It's like, well, I mean, eventually you've got to be able to come back and compare clocks. But in order to come back and compare clocks, somebody has to do something that the other person doesn't do. And that is, they have to turn around. Turning around is the solution to this, because by turning around, you are accelerating. And remember, first principle of relativity, Einstein's first postulate, is that all inertial reference frames are equivalent. But Bob turns around and accelerates. And it's this act of accelerating and turning around that all of the news of everything catches up to Bob, and Bob notices all of the news of everything that happens during those 28 years on Earth during that time. So, including the measurement of Alice's aging. So it is actually true that when Bob comes back, Bob truly is significantly younger than Alice. Alice has aged 24 years more than Bob has. So that is the solution to the twin paradox, one of the other nice paradoxes of relativity. So one can come up with various other little paradoxes on these, but generally speaking, they're solved by the fact that, okay, in order to compare clocks, somebody has to accelerate, or the fact that events that are simultaneous in one reference frame are not simultaneous in another reference frame. Now, one of the big consequences of special relativity, something that Einstein arrived at later in 1905, is the fact that anything that has mass has this internal energy that can potentially be realized if you somehow obliterate the mass completely. For example, collide it with antimatter, that sort of thing. So if I take half a kilogram of matter and collide it with half a kilogram of antimatter, that will be an annihilation of 1 kilogram of mass into energy. And that would be a lot of energy because of the fact that the speed of light is very, very big. So in the case of that 1 kilogram, you're dealing with this like E equals mc squared, so 1 kilogram times c squared. Well, the speed of light is 3 times 10 to the 8 meters per second, so you square that and you get 9 times 10 to the 16 meters squared per second squared. Multiply that by 1 kilogram, and you're going to get 9 times 10 to the 16 joules. And that is over a 20 megaton explosion. So that would be like a hydrogen bomb. And speaking of which, one of the first big realizations of E equals mc squared involves atomic bombs and nuclear weapons. So let's spend a little bit of time talking about that, because that's actually relevant for us talking about how stars get their power. So here's the idea behind how atomic bombs work. So, as you probably know, there are two relatively common isotopes of the element uranium present on Earth. At least if you've paid much attention to a lot of the news lately, you've heard about this because they talk about enriching the uranium and stuff like that. So the most common isotope is uranium-238. Uranium-238 is the most stable isotope of them. It has a half-life of 4.47 billion years, and it therefore is the most common, because uranium-235, the less common isotope, has a half-life of 700 million years. In other words, most of that has decayed down to lead-207 by now. So that's why you have more uranium-238 than uranium-235. Also, uranium-235 is kind of a special nucleus, because if you hit it with a high-energy neutron, it will temporarily become a very unstable uranium-236 nucleus before breaking apart into barium and krypton and extra neutrons, I believe. So this process is what we call nuclear fission. And it so happens that the lighter products, that is the barium, the krypton, and the neutrons, have a slightly smaller mass than the original uranium-235 plus neutron. And that extra mass is realized as energy by E equals mc squared. And in particular, some of that energy is released as heat and radiation, and other of that energy is also put into the kinetic energy of the neutrons, which makes them smash into other uranium-235 nuclei and continues the process. In other words, it is a nuclear chain reaction, and you can get quite a lot of energy from this. Now, the reason you need to enrich uranium is because, again, most uranium is in the form of uranium-238. So what you have to do is you need to liquefy it, that basically melt it, and spin it through these high energy centrifuges to separate out the uranium-238 from the uranium-235, and then keep repeating that process until you have much purer uranium-235. Now, that's one way that you can make an atomic bomb. That's the type of bomb that was exploded over Hiroshima on August 6th of 1945. But another way of doing it is with plutonium-239. You can fire a neutron at plutonium-239, and that makes it unstable plutonium-240. That splits apart into lighter products as well as extra neutrons, and then that continues in another sort of chain reaction of the same type of thing. So that's what was used on Nagasaki in 1945, or August 9th of 1945, and what eventually convinced the Japanese generals, who were the ones who were actually in charge, to surrender. The Emperor Hirohito apparently had been wanting to surrender for a very long time, but he didn't really have much of a say of things back then. But in any case, this can create a very large amount of energy and a very devastating explosion. It was actually a bit of a bluff, because we made the Japanese believe that we might have a bunch more of these nuclear weapons, but it turns out that we were actually completely done after that. We had tested a uranium bomb at Alamogordo in New Mexico earlier in 1945. Then we had our second uranium bomb, which we deployed over in Hiroshima, and then our plutonium bomb over Nagasaki, and that was it. We didn't have any more spares at the time yet, but they didn't know that, so that was what eventually convinced them to surrender. Now, you can also get something much more powerful than this in the form of a hydrogen bomb, where you use a fission bomb, an atomic bomb, to create the necessary heat and pressure to compress together and energize deuterium nuclei combined with lithium nuclei, or deuterium with tritium, that sort of thing, to release energy by turning something that is light into something that is heavy. But the thing that's heavy is actually a little bit lighter than the total stuff that was light that went into it, and that missing mass appears in the form of energy. And these so-called hydrogen bombs are usually on the order of about 1,000 times or so more powerful than your traditional atomic bombs. So consider a large hydrogen bomb with an explosive yield of 15 megatons of TNT. Well, how much mass was realized as energy if 1 ton of TNT has an explosive yield of 4.184 times 10 to the 9 joules? That is 1 billion calories. Well, just do the E equals mc squared bit. First, we need to convert our energy into joules. So, or we can say, okay, our 15 megatons TNT, so we have that as joules, and c squared. Well, we realize that the amount of mass that is there, since E equals mc squared, that means m equals E over c squared. And now you see why we had to convert things to joules, because we're using an SI units equation. We got 0.70 kilograms of mass was realized as energy in that explosion. So just 0.7 kilograms of mass was completely obliterated. Yeah, mass conservation is not a law of nature. It is not a thing. It is approximately true in most chemical reactions, and even there it's only approximately true. If the temperature changes, you're dealing with a little bit of energy realization there. But still, it's not a thing at all when you start talking about nuclear physics. Energy conservation is a thing, where you realize that mass is another type of energy, but mass conservation, nope, it was obliterated. Now, just giving a sense of scale, 15 megatons was the yield of the Castle Bravo hydrogen bomb explosion. Basically, it destroyed one of the Bikini Islands. It no longer exists. So, now you might think, oh, only 0.7 kilograms of material was used for this. No, actually, the material that was used was much more than this. It's just that 0.7 kilograms of that ended up going in energy, while the rest, a lot of the rest was fused. Now here is a picture of a mushroom cloud from the Event Baker blast, which was actually just an atomic bomb, 23 kilotons TNT equivalent. But even here you see that these ships are going up into the stem of that. But imagine something that's 1,000 times more powerful than that. This is a distant picture of the Castle Bravo explosion. And the height of the mushroom clouds it increases as the explosive yield increases as well. So, like the explosions over Hiroshima and Nagasaki might have been something like this. So that mushroom cloud might have gotten up to a height on the order of about 20,000 feet, whereas Castle Bravo got up to something like over 100,000 feet. In fact, the most energetic explosion of all time was the Soviet Tsar Bomba explosion in the early 1960s, which may have been as energetic as 60 megatons of TNT equivalent. And that was an absolutely remarkable blast. They exploded that in, I think, like southwestern Siberia, and maybe it was an island off of northern Russia. But the blast ended up blasting out windows in Finland and also creating a magnitude 6.1 earthquake. So it was an incredible blast. Now, some more stuff about relativity. I mean, we've seen that mass isn't conserved. Well, now it's time to open your eyes to the fact that if you've had physics before, the equation that you learned for momentum was wrong. So P equals mv is the equation that you learned for momentum. Momentum equals mass times velocity. We also talked about it in this class back in an earlier unit. But it turns out this is only true if you're in a reference frame and the object itself is in a reference frame that's traveling at a low percentage of the speed of light compared with the measured velocity. In general, the real equation is P equals gamma mv, where I mentioned that gamma factor before in length contraction. The contracted length is equal to the original length divided by gamma. But this 1 over square root of 1 minus v squared over c squared and just square root of 1 minus v squared over c squared, it shows up so much in relativity that people eventually got tired of writing it, so they just wrote the when it's in the denominator is gamma, because this itself is what we often call the time dilation factor. So something's going at 99% of the speed of light, you end up calculating gamma equals 7. So their watch seems to run 7 times as slowly, and events take 7 times as long according to you as they would take according to them. So we see that if something's going at 99% of the speed of light, P is not equal to mv. It's more like equal to 7 times mv. And as you get closer and closer to the speed of light, the momentum becomes larger and larger compared with the traditional P equals mv calculation. Same thing goes with kinetic energy. Kinetic energy, we imagine that it's 1/2 mv squared, but actually the real formula for it is gamma minus 1 times mc squared. And notice that if you add in the object's rest energy of mc squared, that means that an object's total energy is simply equal to gamma mc squared. But you can see why, especially considering gamma is 1 over the square root of 1 minus v squared over c squared, why we just use the approximation k equals 1/2 mv squared in normal physics classes as well as p equals mv. Because the vast majority of the time, our particles are traveling at small percentages of the speed of light. Now, I did once come across a problem in an AP Physics C E&M textbook where the author apparently did not realize that his electrons were traveling at 30% of the speed of light, and therefore, in calculating the electron's velocity, you actually needed to use the relativistic equation, and you ended up getting a different result because of that. And it was in a chapter before relativity was introduced, so that's why I realized that it was actually a mistake. But it's the type of thing to think about. As long as your particles are going less than about 1/10 of the speed of light, you don't need to use the relativity formulas. But if they're going more than that, you very much do. Now, even if they're going less than that, if you require extremely precise calculations, then you need to use the real equations. I mean, we'll see this again when we get into just basic discussion of general relativity in just a minute. But the point is that as an object's speed approaches the speed of light, the energy approaches infinity, which is why you will never be able to accelerate an object up to the speed of light, because it would require an infinite amount of energy to do so, and a more than infinite amount of energy in order to get it past the speed of light. So that's illegal. Now, as we mentioned before, general relativity is the general situation where gravity is also considered. Now, generally speaking, you can ignore these effects as long as the central mass that is creating the gravity is relatively small, or as long as you're really far away from the object's surface. Now, when we get into black holes, we'll talk about something called the Schwarzschild limit, which I'll just tell you now is about equal to 3 kilometers times the mass of the object in solar masses. So the Schwarzschild radius of our sun would be 3 kilometers. So as long as you're outside of 3 kilometers from the center of our sun, you don't need to worry about it, which the surface of our sun is 6.9 times 10 to the 8 meters, or 6.9 times 10 to the 5th kilometers. So you don't need to worry about it. In fact, you don't need to worry about it at all with our sun, because the amount of mass that is within 3 kilometers is nowhere near the amount that would take it to the Schwarzschild limit. In other words, most of our mass, our sun's mass, is way outside of that. So, in any case, as long as you are more than about 10 times the object's Schwarzschild radius away from it, you don't need to really worry about the effects of general relativity for most calculations. But even with our sun, it does become important when you start looking at things very, very precisely. And we'll get into that in a little bit more detail when we talk about general relativity when we hit black holes. But it does have important implications for the orbit of Mercury. It's a very small deviation, but it's something that is measurable over a time scale of centuries. So let me just show you the Einstein field equations. You definitely do not need to remember this, but this is really a set of matrix equations where each of these so-called matrices is actually a 2x2 or a rank 2 tensor. And the right side of this is really telling you all of the effects of mass and energy that have to do with the object. There's a factor of 8 pi out in front, speed of light to the 4th power in the denominator, and this big G right here is actually Newton's gravitational constant, 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared. But the left is the curvature of space-time. So what this equation is really telling you is that energy and mass tells space-time how to curve. And then when you figure out what to do with this sort of thing, when you really get into relativity, you realize that this ends up going into an equation that tells objects how to move. So space-time does curve due to the effects of mass and energy. So it's something that's important to keep in mind. And in particular, one of the terms in this, the only reason I show this equation at all is because I want to note that the top left term in this T0, in this T mu nu tensor, the T00 term, it's actually pressure. In other words, pressure itself can cause space-time to curve. That's going to have very important implications when we talk about white dwarf stars and neutron stars farther on in this unit. So, hope that was a good introduction to some of the effects of relativity. And if you have any questions or comments, please leave them in the comment section on YouTube. And thank you for watching.